Hello everyone, welcome to this lecture. So, in this lecture we will continue our discussion regarding the perfectly secure VSS based on bivariate polynomials which we had designed in the last lecture, and we will do a rigorous analysis of the protocol. Okay. So, let me quickly go through the protocol steps once again. So, it is a 5 round protocol where in the first round dealer picks a random bivariate polynomial of degree t whose constant term is the secret s, and then it distributes the row and column polynomials to the respective parties, and then in the rest of the protocol the parties interact and publicly verify whether the dealer has distributed consistent row and column polynomials lying on a single t degree bivariate polynomial. So, during round 2 the parties start the pairwise consistency check between their row and column polynomials, and the result of the pairwise consistency check is the results of the pairwise consistency check are made public during the round 3. Okay. So, the first and the second round everything happens over the point to point channels, no public communication happens, and the public communication starts happening from the third round onwards. Namely, during the third round the results of the pairwise consistency check are made public between every pair of parties either in the form of OK messages or NOK messages. Now, for every dispute between party Pi and Pj which has been made public through the NOK message, the complainee, complainant and the dealer make public their respective version of the disputed points during the round 4. So, this again requires broadcast channel. Well, the complainee's version of the disputed points would have been already available through the NOK messages during round 3. The complainant's version and the dealer's version will be available during round 4. Based on that, the parties publicly decide the set of happy and unhappy parties, and now if there are more than t unhappy parties, then we can show that the dealer is corrupt, and that is why it is safe to discard the dealer and terminate the sharing phase protocol with some default summit sharing of 0, where the shares of all the honest parties will be set to 0. But if the number of unhappy parties is up to t, then we have this fifth round where the dealer has to ensure that even the potentially honest parties in the unhappy set, they receive their right row and column polynomials, and this is done by asking the dealer to make public their row and column polynomials. But to ensure that even a potentially corrupt dealer makes public the right row and column polynomials, we also ask the happy parties to make public their version of the common points on these row and column polynomials, and then we check whether the dealer's polynomials is pairwise consistent with at least 2t plus 1 points which are made public by the happy parties. If this condition is not satisfied, then again we can show that the dealer is corrupt. So, it is safe to discard the dealer and terminate the sharing phase protocol with some default sharing of 0. Otherwise, the parties proceed to output their shares depending upon whether they are part of the happy set or unhappy set. If a party is a part of the unhappy set, then it takes the column polynomial which dealer has made public during round 5 and take the constant term of that polynomial as its share, whereas if the party is present in the happy set, then it sticks to the column polynomial which it has received during the round 1 of the protocol and output the constant term of that polynomial as its share. So, that is a 5 round protocol. Now, we are going to prove the correctness, privacy and a strong commitment property here. So, let us first prove a bunch of properties for the case of honest dealer. So, we first claim that an honest dealer is never discarded in this protocol. Okay. If the dealer is honest and it follows the protocol instructions, whatever steps have been assigned for the dealer, if it follows those steps honestly, then it will never be discarded. So, For this we observe that if the dealer is honest, then every pair of honest parties Pi and Pj will be pairwise consistent, and as a result the honest party Pi will make public an OK message for Pj, and Pj also will make public an OK message for Pi. As a result, there will be no dispute between any pair of honest Pi and Pj. That means, if at all there is a dispute between I and j, then it is either because Pi is corrupt or Pj is corrupt, at least one of them is corrupt, assuming that the dealer is honest. That means, when the dealer will resolve the complaints during round 4, okay, then if the complainee is honest, okay, if the complainee is honest and the dealer's version of the disputed points will match the complainee's version of the disputed points, and the complainee and honest complainee will not make it to the unhappy set, it will always be in the happy set. So, no honest party will make it to the unhappy set. So, if at all there is any unhappy party, it is bound to be a corrupt party. And how many corrupt parties we can have in the system? We can have up to t corrupt parties, and as a result of this, the set of unhappy parties can take the size at most t. Okay. So, that means, for the case of an honest dealer, this step, this sanity check will not pass, because there could be up to t corrupt parties in the unhappy set. There can't be any happy, there can't be any honest party in the unhappy set, only the corrupt parties will make it to the unhappy set, and this, since there could be up to t corrupt parties, this condition will never be satisfied for the case of honest dealer. However, that is not the only sanity check, we also have another sanity check. Now, let us see whether this check passes for the honest dealer. So, it is easy to see that this check also will not pass if the dealer is honest, because if the dealer is honest, there will be at least 2t plus 1 honest parties who will be happy, who will be outside the unhappy set. This is because all the honest parties will be outside the happy set, will be outside the unhappy set. That means, they are happy. That means, the polynomials which are made public by the dealer during the round 5 correspond only to corrupt parties. So, for every such polynomial, there will be 2t plus 1 honest parties outside the unhappy set, whose corresponding points will also lie on the dealer's polynomials, whatever polynomials dealer is making public, because dealer will be making public their polynomials correctly. Okay. So, that means, this second sanity check will also fail if the dealer is honest, and as a result an honest dealer is never discarded in the protocol. Now, let us prove another property for the honest dealer. So, we claim here that if the dealer is honest, then the view of the adversary remains independent of the dealer's secret. So, view here means whatever information, whatever messages are seen by the adversary, that means, whatever it has sent, whatever it has received, including its own internal randomness and whatever values it has received from the dealer and so on. Okay. That means, whatever that adversary or the corrupt parties has seen throughout the protocol, that is the view of the adversary. So, the claim here is that the view of the adversary is independent of the dealer's secret. So, let us see denotes the set of corrupt parties. For simplicity, we can assume that the set C includes the first t corrupt parties, but again this is just a simplifying assumption, that will not be always the case. So, what exactly will be the view of the adversary throughout the protocol? The view of the adversary throughout the protocol will consist of only the row and column polynomials corresponding to those t corrupt parties. Let us see why. During the first round, the t corrupt parties will receive the row and column polynomials from the dealer itself directly. So, that is included in adversary's view. Now, during round 2, imagine party Pj is corrupt and party Pi is honest. Now, from Pi, Pj would be receiving 2 common points Aij, Bij, but these points are already included in adversary's point, because these points also lie on Pj's rows and column polynomials. So, that means whatever information Pj is receiving from every honest Pi as part of the pairwise consistency check during the second round, that is not a new information, that is already included in adversary's view, that can be already derived from adversary's view. So, that means no new information, no new content can be added to adversary's view during round 2. Now, let us see anything new gets added to adversary's view during round 3. So, during round 3 what happens? So, every party either makes public an NOK message or an OK message, that does not tell anything about honest parties polynomials, that does not, that means that does not help to add anything regarding honest parties polynomials to the adversary's view. Now, let us see if anything new gets added to adversary's view during the round 4, and the answer is no, because even though during round 4 dealer is making public some points and complainants are making some points public, those points are already known to the adversary. More precisely, if there is a conflict between I and j, at least one of them is honest, if at least one of them is corrupt, because we are considering the case when the dealer is honest, and if the dealer is honest, there won't be any conflict between any pair of honest parties. So, if at all there is a conflict between I and j, that means one of them is corrupt, and that means whatever points dealer and the complainants are making public, that is already known to the adversary, which can be derived from the row and column polynomials of the corrupt parties. So, this is not a new information. And again during round 5, whatever polynomials, whatever points are made public, they can be again derived from the view of the adversary itself, namely these T row and column polynomials. So, that is why we can safely conclude that the view of the adversary throughout the protocol consists of at most T and row column polynomials lying on a random T degree bivariate polynomial. Okay. Now, we can invoke the privacy lemma, which we had proved in the context of bivariate polynomial, and conclude that given up to T row and column polynomials derived from a random T degree bivariate polynomial, the distribution, the probability distribution of those T row and column polynomials will be independent of the constant term of the bivariate polynomial, and that proved this claim. The third claim is that if the dealer is honest, then every honest party Pi outputs the share Si, which is the value of the Samir sharing polynomial f of x, which the dealer has picked during round 1 at x equal to alpha I, and this directly proves the correctness property for the VSS scheme, right. So, let us see why this claim is true. So, every honest Pi would have received the row and column polynomials, sorry for this typo, this should be capital X. So, every honest party would have received the row and column polynomials lying on the bivariate polynomial f of x y from the dealer, and as we have shown that if the dealer is honest, every honest party will belong to the happy set, they will never be a part of the unhappy set, and as a result every honest party will output the column constant term of the column polynomial received from the dealer during round 1. So, the share of every honest party will be this value, and because of the way dealer has picked the polynomials based on its Samir sharing polynomial, and the way that Samir sharing polynomial has been embedded in the bivariate polynomial, it is easy to see that the share S of I is same as the value of the Samir sharing polynomial evaluated at x equal to alpha I. So, this automatically implies the correctness of the VSS scheme, and the previous claim basically implies the privacy of the VSS scheme. Now, let us prove the strong commitment property, which was missing in the simple VSS scheme, where we had just this round 1. assuming an honest dealer. Okay. So, recall that we started with the simpler VSS scheme which had only this round 1 and where we assumed that the dealer is honest, and for that scheme we had proved that the correctness and the privacy properties are achieved, but we also realized that the strong commitment is not achieved. So, to achieve the strong commitment we have now added these 4 rounds where the parties are publicly verify whether dealer has distributed consistent row and column polynomials, and now we want to prove that because of this additional rounds where the parties are publicly verifying their respective polynomials, disputes are raised, complaints are made, complaints are resolved. Based on all these things we will now want to show that a strong commitment property is achieved, for which we have to consider a potentially corrupt dealer. So, we want to show here that if the dealer is corrupt, then at the end of the sharing phase there exists some t degree Shamir sharing polynomial f of x such that every honest party pi outputs a share which is the value of this Shamir sharing polynomial at x equal to alpha I. That is what we want to show. If we show this property, then what we are showing is that this VSS scheme ensures that whatever an honest dealer is supposed to do, even a potentially corrupt dealer is also doing the same. Okay. It cannot deviate. So, there are 2 possible cases here for proving this claim depending upon whether the dealer gets discarded or not in the protocol. So, if the dealer gets discarded in the protocol, then the claim is trivial, because in this case every party takes a default Shamir sharing of 0. That means, in that case we can consider the Shamir sharing polynomial to be a t degree polynomial where all the coefficients including the constant term is 0 and where the share of every honest party is the value 0, which is nothing but the value of this default Shamir sharing polynomial at x equal to alpha I. That means, in that case our Shamir sharing polynomial will be this t degree polynomial where all the coefficients including the constant term is 0. Whereas, the second case for proving this claim is when the dealer is not discarded, which is the trickier case. Now, if the dealer is not discarded, that means definitely this sanity check fails. That means there could be up to t unhappy parties, not more than t unhappy parties. And remember, we are working in the setting where t is less than n by 3. And there are at least n minus t honest parties and up to t corrupt parties. So, if there are at most t parties in the unhappy set, then it also implies that there are at least 2 t plus 1 parties outside the unhappy set, and among those 2 t plus 1 parties outside the unhappy set, at least t plus 1 will be honest, right. Now, what we can say about the row and column polynomials of those honest parties outside the unhappy set? We can say that they are pairwise consistent. There is absolutely no dispute between the row and column polynomials of those honest parties. Namely, for every honest pi and pj who does not belongs to the unhappy set, we can simply say that f I evaluated at alpha j is same as g j evaluated at alpha I, because if this condition would not have been satisfied, then there would have been a dispute between I and j, and then based on what dealer makes public during the round 4, either pi will end up in the unhappy set or pj ends up in the unhappy set. But at the first place we are assuming that neither pi nor pj are in the unhappy set. So, if pi and pj are outside the unhappy set, that means there was absolutely no dispute between their row and column polynomials with respect to the supposedly common points. That means this condition is satisfied. And as we are arguing that there are such at least t plus 1 or more number of such honest parties who are honest and who are outside the unhappy set, and since their row and column polynomials are pairwise consistent, we can now trigger the pairwise consistency lemma and conclude that their polynomials, their row and column polynomials lie on a single t degree bivariate polynomial. Let us call that bivariate polynomial as f star of x y. Okay. Now, we next claim that even the honest parties who are in the unhappy set, their polynomials finally also lie on this t degree bivariate polynomial f star. Let us see why. So, for every potential honest party who is present in this unhappy set, their final polynomials are the polynomials which dealer makes public during round 5. We want to argue that all those polynomials also lie on f star x y. Now, since the dealer is not discarded, that means this second sanity check which the parties have verified, which parties have checked at the end of round 5 fails. Okay. That means, whatever polynomials dealer has made public for pi during round 5, they are consistent with at least 2t plus 1 points which are made public by the parties outside the unhappy set. Now, among those parties Pj outside the unhappy set, how many are guaranteed to be honest? At least t plus 1, because the pairwise consistency check should hold with respect to 2t plus 1 parties, up to t of them may be corrupt. So, at least t plus 1 honest parties Pj are there outside the unhappy set, for which this condition would have been satisfied. So, let us denote the polynomials which have been made public by the dealer by this small fi and small gi. So, these are the polynomials which have been made public by the dealer, okay, corresponding to the party pi, and the party Pj who are honest and who are outside the unhappy set, they would have made public these points. Now, these points which have been made public by Pj, they are nothing but they are points on the bivariate polynomial f star, namely the points lying on their column and row polynomials respectively. And how many such honest parties Pj's outside the unhappy set are there for which this condition holds? At least t plus 1, because the condition is true for 2t plus 1 parties. Up to t corrupt parties who are outside the unhappy set, they may unnecessarily broadcast some points which are pairwise consistent with the dealer's version of the polynomials. We ignore those points. Even if we ignore those points, we are guaranteed to have at least t plus 1 honest parties Pj outside the unhappy set whose points matches, whose points match or whose points are pairwise consistent with the polynomials which dealer has made public. That automatically implies that whatever polynomial dealer has made public for this unhappy parties pi also lie on the f star polynomial because of this condition, and the fact that there are t plus 1 such Pj's for which this condition holds. So, we can't have two different t degree polynomials having t plus 1 or more number of common points. So, if at all this condition is satisfied, that means we have dealer's polynomial fi of x, dealer's polynomial gi of y, and we have this polynomials f star of x of alpha y, right. So, these points are nothing but points on f star of x of alpha I and f star of alpha I y. So, basically we are showing here that whatever polynomials dealer has made public, they are same as the supposedly ith row and ith column polynomial lying on this bivariate polynomial f star of x y. Okay. So, what we have shown now till now. So, we have shown we have started with the fact that the polynomials of all honest parties outside the unhappy set, they lie on some t degree bivariate polynomial f star. And now we have shown that because of this sanity check which the parties are applying at the end of round 5, even a potentially corrupt dealer is forced to make public polynomials of the behalf of honest unhappy parties, which also lie on the same f star of x 5 bivariate polynomial. Now, let us take this polynomial f star of x 0 and we call that polynomial as f of x. What was the claim statement? The claim statement was that there exists some t degree summit sharing polynomial such that the shares which are output by every honest party lies on that summit sharing polynomial. We define that summit sharing polynomial for the corrupt dealer to be the bivariate polynomial f star evaluated at y equal to 0. So, it is guaranteed to be a t degree polynomial. This is because f star is guaranteed to be a t degree bivariate polynomial. Now, what exactly are the shares of the honest parties? Well, it depends upon whether the honest party pi is in the unhappy set or whether it is outside the unhappy set. If it is outside the unhappy set, then it will stick to its column polynomial and output the constant term of that column polynomial as its share. But we have already argued that such column polynomials g I of y is nothing but f star of alpha I y, because we have already argued that all the column polynomials and row polynomials of the honest parties lie on f star of x y. This automatically implies that the share S I of every pi not belonging to the unhappy set is nothing but this value, and this value is nothing but the value of our this defined summit sharing polynomial at x equal to alpha I. Whereas, consider those honest parties pi who are unhappy. For them, we have to take the dealer's version of the column polynomial made public during round 5, but fortunately for those column polynomials also we know that they lie on f star of x y as well. So, whatever argument we have run for the honest pi's outside unhappy set, we can run for the honest pi's in the unhappy set, and we can conclude that their shares are also the evaluation of this defined summit sharing polynomial at x equal to alpha I. So, that concludes the proof of this claim, and that also concludes the proof of this strong commitment property. Now, let us do the complexity analysis of this VSS scheme. How many rounds are there in the protocol? We have 5 rounds here in the protocol. The first 2 rounds involve only communication over the pairwise channels, but in the round 3 we have the broadcast channel invoked, round 4 also broadcast channel invoked, round 5 also broadcast channel invoked. An interesting question is, can we reduce the number of rounds? Why we are interested to reduce the number of rounds? Because every time the parties need to interact, they have to send messages. So, if the parties are geographically very isolated, then we will prefer a protocol where the number of interaction among the parties is less. So, in the next lecture we will see a very cute technique to reduce the number of rounds from 5 to 4, and one can show that the optimal number of rounds for any perfectly secure VSS scheme in the sharing phase is 3 rounds. We will not be going through the 3 round protocol because that is quite challenging. We will see in the next lecture a 4 round version of this current VSS scheme. Let us do the communication complexity analysis. How much communication is done by the honest parties here? So, over the point to point channels, n square log of field size number of bits are communicated, because dealer has to communicate the row and column polynomials to every party, single party, and then there between every pair of parties pi and pj 2 values are communicated over the point to point channels as part of the pairwise consistency check. So, that involves the communication over the point to point channel. Over the broadcast channel, also we have a communication of n square log of field size number of bits. This is because there could be up to t parties in the unhappy set, and for every unhappy party, dealer makes public the row and column polynomials. So, the row polynomial will be a t degree polynomial. So, it will be represented by t plus 1 field elements, because those will be the coefficients of the polynomial. So, t plus 1 field elements. So, altogether order of n times t field elements may be broadcasted by the dealer, and since we are working with the condition t less than n over 3. So, asymptotically t is always order of n. So, order of n square field elements are broadcasted, and each field element can be represented by log of field size number of bits. So, in terms of bits, that is the amount of communication done over the broadcast channel. Now, recall that to emulate one single broadcast, we can run an instance of the reliable broadcast protocol. So, after emulating all the broadcasts in this protocol through an efficient polynomial time reliable broadcast protocol, say the phase king protocol, we get that the total communication complexity of the protocol is n power 4 times log of field size number of bits. That is the communication over the point to point channels after emulating all the broadcasts in the protocol. So, with that I end this lecture. Now, we have a perfectly secure VSS scheme with n greater than 3t, where we can achieve the correctness and the privacy property against for an honest dealer, and also we can achieve the strong commitment property against a potentially corrupt dealer. So, these are the references used for today's lecture. Thank you.